Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we will be talking about semiconductor manufacturing, one of the key driver for precision machines. So, as we know and we see that the chips are everywhere. The consumer products we have, our phones, mobile devices, watches, laptops, computers, home appliances, even the scientific instruments, the medical robotics, and even our cars, they cannot run without the chips. So, these semiconductor chips are everywhere, and that is one of the reasons why we are talking about the manufacturing of the chips today, and how this precision machine, or in a way design of precision machines, this course is relevant to achieve these products. So, what we see here, that the number of ICs on a chip is growing more and more, and initially it was very few, but in today's time it has many. And way back in 1965, the gentleman Gordon Moore observed that every year the number of ICs in a chip, they are going to be doubled. Later he rectified, and he said every second year it will be doubled, and this is what you see. And later he became one of the co-founder of Intel. So, what you observe here, like in 1959, Fairchild Semiconductor, they produced the first chip of the size of a fingernail, and you see the first integrated circuit on silicon on a wafer. But now if you see in 2012, and now if we see the number of transistor on a chip, and the size of the chip is same, it has increased tremendously, almost a million times, and you have now billion transistor on the same chip. And what Intel has projected by 2030, there will be 1 trillion transistor in a chip. So, you can see how things are moving, and it's not like the size of the chip is increasing, but the size of the transistors are decreasing, and we are cramping all those transistors in the same footprint, and the size is almost the same as the size of a fingernail tip. So, if you want to get a very good overview of semiconductor industry and how this has evolved, this is a very good read. You can read this book, Chip War by Chris Miller. And what we realize that in today's time, the semiconductors is the new oil, right? Is the driving everything. So, if for some reason, if the semiconductor industry gets affected, and if you are not getting the chips in time, if it's not delivered, actually nothing will move, because it affects the production of each and every product, every machine, every equipment we are using today. So, this is very good introduction, and it talks about the evolution. So, how it has started way back in 1959 from Bell Labs and from America, and then how it has moved to Asia, Japan, then Korea, so you have Samsung. In Taiwan is TSMC. So yes, geopolitical things have affected, and but you think most of the countries are involved in semiconductor manufacturing, and one of the key component or key processes is lithography, which is dominated by ASML in Netherlands. So if you want to have a good overview, please go through this and read this book. We are also not behind, though we started late, but the government has just started India Semiconductor Mission now, and the emphasis is to build semiconductor and display ecosystem, positioning India as a global hub for electronics manufacturing and design. And under this initiative, there are already 76,000 crore invested, and there are 5 projects approved for semiconductor and display manufacturing ecosystem in India. So, are we ready for that, or are we simply relying on the devices, on the instruments or the machines built elsewhere? If semiconductor manufacturing is coming to India, what kind of support we can provide, whether we can design, develop systems for our own use, whether the manpower, whether the know-how is with us, so that we are not totally dependent on others, but we can develop these systems and slowly localize the manufacturing of these semiconductors here in India. So, I think it is very important to understand what is the semiconductor manufacturing ecosystem looks like. So, there are several processes. So, we have wafers, then a lot of wafer makers will be involved. There are several processes: cleaning, deposition, lithography, etching, CMP, packaging. So, the academia has a bigger role to play. We need to train people so that we understand the process, and based on the process requirement, we should be able to develop machines, systems, and even for inspection and metrology. So, there will be materials manufacturers and facility development. So, are we going to support all these activities, whether we have enough manpower with the sufficient know-how and knowledge? I think this course is one of the steps towards that. So, first try to understand how these chips are made, and if you do not know, you may be surprised to know that the raw material for the chips is actually sand. So, we start with the sand, and then it is melted, and we try to get pure silicon in its purest form, and then you convert into silicon ingots, and then it has to be sliced into thin wafers, and this will be the wafer will be the, I think, input material, which undergoes a lot of chemical processes, different kind of processes under different kind of machines, and ultimately chips will be delivered. So, going further, what we realize that we start with the silicon ingot. So, we do the slicing there, first slicing, and the quality of these wafers created may not be very good. So, it has to be polished to the requirements. The order of thickness of these wafers might be about 700 to 800 microns. So we will go through various processes after that. So there will be a lot of material depositions and modifications. So and then we prepare it for lithography. So there will be photoresist coating and it will go for exposure. So this is the critical step and a lot of precision machines involved here. So it's very much like photography. So we have masks. So the design will be there. So and there will be optics involved and then it will be signed on an individual chip. And then once it's done, there will be developing and baking and those many chemical processes. So like etching, ion implantation, we will remove the photoresist. Yes, and then there will be many cycles, repeated cycles we will be doing because we will be creating layers and layers. And then once the entire process is done and it's completed, then we get the completed wafer. And this wafer have many chips. So they will be separated, diced, and then these individual chips will be packaged and we will get the devices what we have. So each and every step is very intricate and involves a lot of precision processing and precision instrument, machines, equipments. So if we try to characterize, we can divide into different kind of processes. Usually one is called front end processes which involve lithography operations. So what do you see here? Many cycles we have. So as I just mentioned in the previous slide, okay, we have this wafer and then there will be oxidation, diffusion. So we do a lot of chemical processes. Then we have this wafer. So thin film layer will be put there and then ultimately lithography, it will come under the lithography system and the design will be shined and will do the developing, etching and implantation and it will be repeated through many cycles. And then we have this metal wiring will be done. So again it's also a kind of a deposition only, deposition process. And then once it's done, the dicing will be done. So we will get the individual chips. So the assembly process, this all generally termed as back end processes. So we take this individual chip, then die bonding will be here, then wire bonding, mold, plating and then okay, it will be individually tested and we will get the device, the chip. So many processes are involved and we need to understand how these processes are performed, what are the process requirements and whether the machines what we have or want to develop, whether they can meet those requirements. So lithography is one of the critical steps and as I mentioned, that is more like a photography. So printing the circuit design onto the wafer. So we have a light source. So it is signed on a mask. So mask has the IC design, what we want to put on the chip, and there are lens system. Through the lens, it will be projected on the wafer and chip pattern will be made on the wafer. And you can see there are many chips. So one single wafer can have many chips and there are a lot of chemical process involved explained here. So we may not be going into the details. We simply want to understand what are the processes and what are the requirements, so that we understand what kind of numbers we are working with, what kind of mechanical specification, design specification we want to have. So, that is the front end process. So, but once the chips are made on the wafer, it has to be inspected. So, each and every chip has to be inspected. We do not want to have any kind of defected piece. So, it is 100% inspection. So, there are a lot of processes again involved. There are wafer inspection systems, and of course, if we want to increase the yield, the process cannot be slow. It has to be very fast, but at the same time it has to be very accurate. So, under the wafer inspection system, the wafer has to go through every chip has to be inspected, and the defected chip, it has to be thrown out. So, once we have all the chips inspected on the wafer, as I mentioned, in a single wafer we can have many chips. So, it will be diced, and then later it will go to the device. So, that single chip will be covered in a resin package, and then later we will have a like wire bonding, and those processes will be there, and then we will get the semiconductor product. So, let us have a look inside a chip. So, usually the size of a wafer is about 300 millimeter diameter, and the size of a chip is maybe of the order of 5 to 10 millimeter by 10 millimeter, or even smaller. And how these billion transistors are built on a chip. So, we just try to understand. So, the wafer you see, as we zoom in, we are zooming to a chip level, and now we can see the individual circuits, the ICs, and if we go further, what we realize that there are many and many layers. So, many layers, and they are interconnections, so metallic connections are there. So, it is like creating a 100-story building with the plumbing, with the electrical connection precisely, so that it function well. The only difference is the size now we are talking about is it will be within a size of a fingernail, what we can say 5 to 5 or 10 by 10 millimeter square area we are talking about, and we have to create these structures precisely to that level. So, we also try to understand the machines. So, SML is producing the state of the art lithographic systems, and it is very nice to see these systems and understand what are the precision requirements of this system. So, we will go through that, and we will watch a small video of the system here.
A chip is a tiny skyscraper. Its circuitry often includes billions of transistors and stretches through more than 100 layers, and every structure needs to connect perfectly. At ASML, we build hardware and software that helps our customers mass produce this microscopic circuitry. Our lithography systems print chip patterns by shining light from a source onto a blueprint or mask, and then harnessing that light with optics to transfer the patterns to silicon wafers. But in the world of nanometers, physical and chemical processes deform the pattern. So as chip features continue to shrink, lithography becomes more challenging and more crucial. As lithography experts, we fundamentally understand the processes that influence chip patterning, and we develop models and algorithms that predict how a pattern will print on a wafer. Using these insights, we can then adjust for any deformations and tune the lithography system to produce the best possible image. We call this computational lithography. First, our source optimization tools meticulously adjust the illumination to produce sharper images of critical chip features. Our mask optimization tools design masks that correct for optical effects, so chip patterns appear exactly as intended on the wafer. Light heats and deforms the optics, so our wavefront optimization tools reshape the light once more to ensure that the pattern prints correctly. And we do this pattern by pattern, layer by layer, chip by chip, wafer by wafer, at the volume, speed and robustness our customers need for mass production. As these tiny skyscrapers continue to grow and their features continue to shrink, our task only gets harder. But we're up to the challenge. We're committed to powering technology forward with you.
So, if we try to understand the entire processes, so not only the lithography systems, but once chips are made, how is packaged, what kind of the inspection systems, what are the other processes involved. So, we will also can look into Taiwan's mega factory, that is TSMC. So, one of the foundries there for semiconductor, and we get a very good sense here, like what are the technology requirement. And if you want to support the semiconductor mission here in India, we also need to upgrade ourselves. We need to understand what is the design philosophy to create those machines and what are the efforts required. So, not only to service or support the machines what we get from abroad, from Netherlands, from US, from Japan, from Taiwan, but at the same time we may also like to develop these systems here to support Make in India effort, so that we can design ourselves, make systems, and we can definitely get cost benefit, but at the same time we maintain the same quality. So, if we look at the architecture of a typical lithography system, it's from ASML. So, one is here you have the illuminator, so which directs the exposure light to the reticle stage. The pattern on the reticle then projected through projection lens on the wafer, which is located on the wafer stage here. The wafer handler here exchanges the wafer after each exposure, while the reticle handler exchanges the reticle for each different layer, what is required for the IC design. So, there are several steps and several modules I would say, and it is a very modular design. So, it does not affect the entire system. So, if one module is affected and suppose it is not functioning well, it can be easily replaced by another one. And these systems, they have to run continuously without any break, because moment if there is a breakdown, it will affect the process, it affects the yield, and therefore, the cost of the chip will increase. So, here what we want is the cost of the chip should not increase, and thereby we are able to afford all these system with these powerful chips. So, once designed, this is how it look like. So, this is the latest extreme UV setup from ASML. So, when we look into the mechanical design and go into the details, what we realize that a lot of dynamics involved. At the same time, it is a very deterministic system, and there is a metrology frame, there is you have air mounts, and the reticle stays, the wafer stays, they are moving precisely to the nano level, and what one may realize that these systems are actually floating. There is no physical contact with the ground, and even the ground vibrations are limited. The entire system is actually floating and isolated from ground vibrations. But at the same time, these systems are moving at a very high speed. So, it has a well defined dynamics and the control. So, a lot of mechanical development required here. We need to work on the actuator dynamics. So, there are longer stroke, shorter stroke motors, there are air mounts. So, all those challenges, all those key aspects we have to look into, we have to work on them. The challenges are here with such a high speed moving systems, how to maintain the accuracy. Yes, the speed and acceleration definitely very high. How to achieve thermal stability and crash robustness. So, to get an idea about the acceleration and how fast these systems are moving, we can just compare. So, if something drops, a stone drops with 1 g, that is 9.8 meter per second square. We have dragaster which moves at 3 g, 33 meter per second square. We have a jet fighter with the 4 g acceleration. The twin scan which already moves at 88 meter per second square, which is 8 g or roughly 9 g we can say. A missile 50 to 120, so 5 to 12 g. And the reticle stage which is used in this ASML system or lithography systems, the target is already to reach 15 g. So, they are even moving with that high acceleration. So, how to maintain the dynamics, how the dynamics is there, and how to control and how to achieve the precision, the accuracy level required in these systems, even though if it is moving at a very high speed with a very high acceleration. So, this is the state of the art, this is what we get, and what we need to understand that if we really want to support the semiconductor industry, it is not just the design of the chips, but how to get that chip design on a silicon wafer and then to a chip. The manufacturing aspect, the mechanical design aspects, the control, electronics, the entire engineering community, I think they need to work together and they need to solve this problem so that we can at least support these facilities, and later we can create our own systems to support the manufacturing, semiconductor manufacturing in India. So again, different elements, and this is old number, $140 million, which is roughly 1,200 crores, but the latest system is even more. So one can expect that what is the value proposition and what is the cost of building these systems. So a small effort may not be enough. I think effort from the industry, from the academia, and it's from the government that is required to build such facilities and to run these facilities in a good way. The other side, once the chips are made, once the wafer is complete, again it has to go through various processes, which I mentioned in the beginning, which is we term as back-end processes. So for inspection, wafer inspection and metrology, as we mentioned, there are many chips on a single wafer, and each chip has to be inspected for quality and validated, and in a super fast way. So how to achieve that? So what are the key elements? So if we check this, the key enabler is these motion stages, XY motion stages many times. So I think this is one of the key objective of this course. We should be able to design these motion stages, achieving those precision level of the order of not microns only, but it should go to nanometer levels. So therefore, it's a very important to understand the requirements, what are the design principles for precision machines, whether conventional design can produce these systems, and many times we realize that that may not be enough. There are very different thoughts, very different design philosophy. We may know, the senior designers, the experienced designers, they know through the practice, but all these learnings, these principles, it has to be taught right from the beginning, so that once you graduate, once you complete these kind of courses, you should be able to appreciate and understand how these systems are built, and later also apply these philosophy to design state-of-the-art machines and even the consumer products for today's use. Because at the end of the day, even the normal machining, normal processes, they also need high precision. So we try to understand each and every component of a precision machine, how to achieve that, what are the design principles, and as we mentioned, we try to bring the deterministic behavior into our design. So through understanding degrees of freedom and constraints requirement, what is the exact constraint design, what happens if we have over constraint design, what exactly it means, we will go through that. We will try to learn about compliant mechanisms, air bearings, linear motors, and dynamics and control. So from the next lecture, we will try to go through different topics one by one. I hope we have enough background now, enough understanding why we want to go ahead with this course, why this course is important if you want to design precision machines for semiconductor application, for designing machines, for measurements to the nanometer level, design robotic systems for reliability, for safety, design products without failure, design systems with the high quality, high reliability, and definitely at a affordable price. So, we will start these topics one by one from the next lecture. Thank you.